then you may ask, so why do we need to talk about error grade? Again, we talk about error grade not because we want to use error grade. We talk about error grade because we want to understand error grade, and then we are going to use that. I mean, the concept, okay, will be applied to the following optimizer. Okay, so this concept, okay, is applied to the next optimizer. Actually, next two optimizers. Okay, so let me first show you, okay, why we have like the gradient gets like become too small, because S is initialized as 0 at beginning. Okay, so even though we add up this value, but at this value, okay, it's going to subtract each gradient. Okay, so really like the subtraction. This subtraction term is too big. Okay, and so that's a problem. So what we want is we want to do a little better job here. Okay, so here comes the RMS prop. Okay, so RMS prop, okay, it's slowed down too fast, right? So instead of doing that, you can see this formula. This is the formula for RMS prop. You can see this is almost identical to the error grade, except that here we use what we call the exponential decay. If you still remember, we talked about exponential decay last time, right? When we talk about how we can compute the average for the whole class. Remember? Okay, we use like alpha times like the current average plus 1 minus alpha times like the average of some small sample of students. Okay, and we keep doing that. Eventually, we are going to compute the average for the whole class. If you remember, okay, we talked about that, right? So here, okay, that technique is called like exponential decay. Okay, so now, okay, you can see we apply exponential decay when we compute the S. So by doing so, okay, the S, okay, will not, okay, it's not going to be that, how should I say? Because like in the previous one, okay, you can see this, and initially S is 0. This is almost dominated by this term. But now, okay, we use this beta to control how much is emphasized on the previous S, how much is emphasized on the new coming value. Okay, that's become like a kind of like an average of these two. Okay, so S actually is the beta is typically set to 0.9. Okay, S is still initialized as 0. Okay, so so initially S is not going to be that big. Okay, because 0.9 times S, which is like close to 0, plus like 0.1 times this term. So this term is not going to be that big. But still, like the bigger, the one that has the steeper gradient, the component has with a steeper gradient will still be subtracted by, be divided by a bigger term. Okay, the concept still stays the same. Concept stays the same. So, and also this decay rate beta, okay, typically set to 0.9. So and this is again another hyperparameter, but this default value again normally work very well. So we normally do not intend to tune it. Okay, do not tune it. So how do we implement the RMS prop? Okay, it's like this. There's an RMS prop optimizer. Okay, and in here we have momentum which is the friction, okay, and the decay, okay, and that epsilon value, okay, and here we pretty much put like a default value here, okay, for this RMS prop, and basically RMS prop performed very well, okay, compared with all the optimizers that we have talked about. Actually, before Adam optimizer came out, okay, the RMS prop used to be the best optimizer. Okay, so a lot of time, okay, I mean in the past, a lot of time people just use RMS prop, okay, to be the optimizer. Okay, but that's before the Adam optimizer came around. Okay. So here comes that last one. Okay. Adam optimizer. Adam actually is not named after the person. Okay. You may think Adam optimizer is named after its inventor. No. Adam is a abbreviation of adaptive momentum, adaptive moment estimation. Adaptive moment estimation. Okay, it combines ideas of momentum optimization and then RMS prop. Okay, so you can see, okay, in this formula, if you look at the first line and this part, it's momentum optimizer. If you look at the first line and the first half of the line 5, it's momentum optimizer. Okay. If you look at the second line and the second part of line 5, it's RMS prop. Okay, it's RMS prop. Okay. Of course, line 3 and the line 4, what are they? I will explain later. Okay? I'll explain later. Here, this T is like the exponent. It's an exponent for the beta 1 and beta 2. Okay? And this T stands for the iteration number. I will get to this point later. Okay, but anyway, even though I say the first line and the first half of the line 5 is momentum optimizer, really it's still a little bit different from the momentum optimizer. In the momentum optimizer, we do not have exponential decay here. We do not have exponential decay. Okay, it was assigned n plus beta times the gradient. Okay, if you look at the momentum here, right? Oh, not n. I'm sorry. It's a beta n plus like beta n times plus eta. Okay, times like the gradient. Okay, so this part, okay, is replaced by the exponential decay now. Okay, that's the only difference. Okay, that's the only difference. Okay, and the other part is like I think I already mentioned that. And the steps 3 and 4 are it's mentioned here as somewhat technical detail. Okay, since n and s are initialized at 0, okay, at 0, they will be biased towards 0 at the beginning of the training. So these two steps will help boost n and s at the beginning of the training. Let me explain. Okay, let me explain. Okay. At the very beginning, it's the first iteration, right? At the first iteration, right? Okay, say beta 1 is 0.9. Say beta 1 is 0.9. Okay, this is this 1.1 minus 0.9 is going to be 0.1, right? So 0.1 times this gradient, right? This is 0.9. But remember, this one is, okay, at the beginning it was 0, right? It was 0. So this one gets like only 0.1, right? This thing is multiplied by 0.1 only, right? So it kind of gets discounted a little bit too small, right? Okay, it's discounted a little bit too small, right? So, okay, then 1 minus 0.9 to the power of 1, well, it's still 0.9, right? So it's going to be 0.1, right? N divided by 0.1, what happened? N gets increased by 10 times, right? So this one used to be multiplied by 0.1, right? Now this thing is increased 10 times to be a new N. Okay, this thing is enlarged. This thing is enlarged. Okay, same thing apply for the S. Okay, because initially S was 0. So this is going to be a very small value from here. Okay, but when this value is too small, okay, we may have issue. So this place try to boost this value. Okay, try to restore its original value back. Okay, and then okay, but after a period of time, after the iteration, number of iteration become like a bigger and bigger. What happens? Like remember, this t is going to be big, right? This t is going to increase, right? And this beta 1 and the beta 2, they are both a fraction, right? Either 0.9 or 0.99, right? Okay, when t becomes big, okay, this thing will quickly, become 1, right? Okay, because beta 1 to the power of t will quickly, shrink to 0, right? Right? Beta 2 t to the power of t, beta 1 to the power of t, and beta 2 to the power of t will both shrink to 0 when t increases, right? So in other words, the n is going to be divided by 1, right? So this thing is going to have no effect whatsoever, right? Okay, so when the iteration, okay, keep going, okay, and the later part, the line 3 and line 4 is not going to have any impact. But at the beginning, it helped to boost the n and s to the proper size. Okay, that is what their purpose. This is their purpose. Okay, so you see, these two steps will help boost n and s at the beginning of training. And the momentum decay hyperparameter beta 1 is typically initialized to 0.9. And the scaling decay hyperparameter beta 2, okay, for the RMS part is typically initialized to be it's often initialized to 0.999. So as earlier, the smoothing term, epsilon, is usually initialized to a tiny number. So here we assign, normally assign to be 10 to the power negative 8. So these are the default values for tensor flow, okay, at the optimizer. Okay, so how do we use that? Just optimizer is equal to this added optimizer. Learning rate equal to learning rate. Okay, if you only want to use the default value of these hyperparameters. If you want to tune them, then you have to specify these parameters in order to change their default value. Okay, but Okay, you may argue, well, how about the learning rate? Okay, how about the learning rate? Okay, well, just like add up grade on this plot. Okay, Adam optimizer. Okay, these three optimizers are the adaptive they have adaptive learning rate. Okay, so in other words, okay, these three algorithms require less tuning of the learning rate. So we don't even need to consider the learning rate to be a hyperparameter. You can assign just not like any, but pretty much just assign to a fixed learning rate, such as 0.001. Okay, it would like here. Okay, just default value. It's going to make like Adam much easier to use. Okay, than grading descent, and it's going to perform very, very well. So one thing to talk about is okay, we have talked about this different sort of like optimizers. Okay, so you can see that for all these optimizers, we make use of the first order derivative, right, or the partial derivative, or the gradient, right, or gradient, whatever you call it. Okay, to determine like how to optimize. Okay, so I mean, so